Hi, welcome to the first of our short mini lectures in ECN 4843. Today we're going to cover a very quick review of Maxwell's equations. Now you've had an entire course on electromagnetics and Maxwell's equations before this, and I certainly can't do the subject justice in a 10 to 15 minute mini lecture. So I just want to hit the high points, and I'm going to ask you to please open up your electromagnetics book, recall these things, go back and review these things because they will be somewhat important in this course. We're interested in electromagnetics as it describes light, and there are three ways that you commonly describe light, depending on the type of problem you want to solve. Light, of course, is light. It doesn't care about you, your mathematics, or your problem. It's going to always behave the same way, no matter how you describe it. But it is important to use the correct mathematical technique if you want to do engineering. And one way we do this is if the object that the light's interacting with is much, much bigger than a wavelength of the light, we can treat the light as moving in a straight line as a geometric ray, and that's what we covered when you went through the other course. A second way that we're going to use for the first part of this class is light behaving as a wave, an electromagnetic wave, and so you're going to be asked to recall, and we'll review today the wave properties of electromagnetic waves. And this is fairly complex in some situations, but it's valid for most of the situations you're going to encounter. But we also need to think of the wave-particle duality, the fact that light is not only a wave, but it comes in discrete chunks of energy called photons. And this is going to be very important to understand lasers in the second half of the course. But let's jump into reviewing electromagnetic waves and see how that impacts light in this course very briefly. So we have Maxwell's equations. I'm not going to write them down here. You should have either memorized them, be familiar with them, or have a book close to hand where you can look them up as you need to. And we know if we do some rearrangement of Maxwell's equations, we can come up with what's known as the wave equation, which is given right here. And this wave equation essentially relates the second spatial derivative of a four-dimensional vector that has three spatial dimensions given by the component, and let's grab a highlighter, R. It has one time dimension for 4 dimensions, and it relates the spatial variation to the second derivative of the time variation of that complex vector field, which is the electric field. And if you really have to solve this thing, and this is by far the simplest version of the wave equation, it can be very difficult. So, of course, is in the usual way of differential equations, we look for a solution that somebody has already done for us. We don't have to solve this every time we have a problem. And one of the really nice solutions of this is a plane wave, which in its more complex mathematical form, if you're going to keep all your vector notations and work in 3 spatial dimensions and 1 time dimension, you write like this. But for most common situations, you can simplify to an electric field having a constant amplitude pointing in a particular direction, which we've chosen to be along the y-axis here, but this could be any spatial dimension, multiplied by a phase term. And of course, this equation right here, you'll notice, has the e to the I theta, and let's call that j theta, for example. Magnitude and phase notation we see so often in phasor notations and other engineering applications. This term, of course, in the parentheses, is the phase of the electromagnetic wave. And phase relates space and time. It tells us how the variation of the wave changes with space and also with time. And it's given by omega t, which is the time variation, and kz, which is the space variation, where we're assuming the wave's propagating along the z-axis. You can, of course, expand omega and k into a lot of different formats. The angular frequencies are related to the speed of light and the wavelength. The speed of light is, of course, related to the angular frequency in k, the propagation constant of the wave, and they're also related to the permeability and permittivity of free space, where we're assuming our wave is propagating through a vacuum. And of course, the propagation constant is inversely proportional to the wavelength in free space. And so all the parameters of a wave that you're very familiar with by now are related to this phase. So let's look at a picture here. Of course, there's a real part, which is shown in the blue, and an imaginary part, which is shown in the red. And I actually think in this diagram I accidentally got those backwards, but not to worry about it. Of course, the sinusoidal term, which is blue, should be the imaginary part. So let's go ahead and change that. And we'll go back to our red pen. Fix that. There we go. When we plot this wave, we need to do it on two axes because the phase, which is just the position or where you are in the wave, does vary with both time and space. The spatial variation, of course, is given by the wavelength. So if we go from a trough to trough here, or any 2 points on the wave, it doesn't have to be 2 troughs. One period of the wave in space is the wavelength. One period of the wave in time, where we're measuring from peak to peak here, is essentially inversely proportional to the frequency of the wave. And of course, the height of the wave is the strength of the electric field, or the amplitude, which in our equation right there would just be E naught. Now, I'm going to pause for a second, and we'll stop the video, and I'll open up another application, then restart the video, so you can look and we'll have a brief discussion of what one of these waves really looks like as it varies in space and time, because we need to animate it to do that. It's very hard to visualize this with a static screen like we have. Okay, we should be recording again. I've opened up a browser window, and as you should be able to see here, I've gone to a Java applet on a website that you can copy and explore with on your own, and I've set it to show 3 periods of a moving electromagnetic wave. And because I'm recording, the wave's not moving along very smoothly. Unfortunately, the processing power of my little tablet computer is not enough to do video recording and a smooth animation, but this should be moving smoothly. But there are some things you need to recognize. This is what a propagating electromagnetic wave looks like. You'll notice that if I were to stop the propagation of the wave by hitting the stop command there, that as we move in space, and so let's move one of our planes here, as we move in space, there is a variation of both the electric field and the magnetic field as a function of time. And that's given by the spatial variation of the wave. Certainly the amplitude of the wave is dependent on the position you measure it at. And if I were to fix my planes and then begin the animation again, you'll notice that what happens is at any fixed point in space, the phase or amplitude is changing with time, where the overall, I guess I should say the field strength is time dependent, because the amplitude is constant, the phase is changing with time, and the phase times the amplitude, giving the overall field strength varies.